Why waste time in commute and spend lot of money for iitjee coaching? Parents, do you want your kids to achieve top scores in iitjee? India's leading online NEET coaching 100% success iitjee. At TeenEinstein, we focus on iitjee coaching from class 6 to class 12. We think you'll like it. Our teachers are mostly PhDs in physics, maths, chemistry, botany, and zoology, with lots of years of teaching experience for class 6 to class 12. Thousands of videos, quiz, MCQs. We provide a daily worksheet of 30 questions on each topic: math, physics, chemistry, and biology, for rigorous practice, concept understanding, evaluation, quiz, and thousands of videos. Limited offer 40,000 rupees per year. Book your class. TeenEinstein.com.
Hello everyone. In this video, we are going to talk about electrostatic potential and capacitance. In the previous videos, we already talked about electric charges and static electric charges are giving rise to field and forces between them. And we also studied in detail about the dipoles and what happens to dipole when it is in electric field and how the torque is produced. So in this video, we are going to talk about electrostatic potential. And these are the topics we are going to cover. First, we'll give an introduction. Then what is electrostatic potential and what is the electrostatic potential associated with a point charge. And when we add another point charge, then we get a dipole. So we will see the electrostatic potential of a dipole. Then if we add more number of charges, then we get the system of charges. How the static potential happens when there is a system of charges. Then we will talk about equipotential surfaces, potential energy of a system of charges, and potential energy in an electric field. So there is a difference here. We are talking about electrostatic potential, then we are moving on to another term called potential energy of a system of charges and potential energy in an external electric field. So first, we are going to talk about work done by external forces in moving the charge Q from R to P in this picture. So why we need to talk about the work done here is why there need to be an work done, because this is a positive charge. And in the previous chapters we studied about the field exerted by a positive charge when another test charge is brought into its field, right? So there will be a force exerted by this capital Q on this small q. So in order to bring this Q from R to P, you need to do some extra work, because this is also a positive charge, this is also a positive charge. So this charge is going to obviously repel this charge. So the obvious movement of this Q is to be away from this charge, but we are bringing it opposite. So we are bringing it closer to this charge. So in order to bring this charge from R to P, we are opposing this electric field. So to do work opposing the electric field, we need to give a force in the opposite direction. So this is similar to when you throw a ball up in the air. When you throw a ball up in the air, you are doing some force against gravity. So you are doing some work against this gravity, and this particular work you are doing is stored in terms of gravitational potential energy. So that is why objects at a height have more gravitational potential energy than the objects that are near to ground. So similarly, this Q will have more potential energy at this point P in compared to the point R. So okay, before going into all this, we will see what is the work done in this case. So we know the definition for work done. Work done is going to be force multiplied by the distance along the same line. So in this case, work done from in bringing this charge from from R to P is going to be integral of R to P F external dot dr. And why we say it is F external? Because the work is done by an external force and not by this electric field, because the electric field is pushing it away, not bringing it closer. So to bring it from R to P, the work done multiplied by dr. Dr is the distance that is traveled. And then in the next step, we see here minus and Fe. So why it is minus Fe? Because in order to bring this from R to P, you're exerting a force which is equal to this electric force, but in the opposite direction. So that is why work done by this electric field now is negative in this case. Now, at every point in electric field, a particle with charge q possesses a certain electrostatic potential energy. This work done increases its potential energy by an amount equal to potential energy difference between the points r and p. The potential energy difference is given by delta u equal to up minus ur equal to wrp. So, what they are saying here is, the particle q, the charged particle q, will have a particular potential energy here, and it will have a particular potential energy here. In this case, at the point P, it will have a higher potential energy. So what is the difference between the potential energy? That is up minus ur is nothing but the work done. So potential energy difference between 2 points is equal to the amount of work done in bringing the charge from one point to another. So that is the definition of electrostatic potential energy or potential difference. Okay, so electric potential energy difference between 2 points as the work required to be done by an external force in moving a charge from q from one point to another for electric field of any arbitrary configuration. So this is how we define electrical potential energy difference. So between any 2 points is defined as the work required to be done by an external force in moving the charge q from one point to another against the electric field. That electric field could have been given by any arbitrary charge configuration. So the work done by an external electric field in moving a charge from one point to another depends only on the initial and final points and is independent of the path taken to go from one point to the other, and this is called conservative force. So when for example, in this case, we can take this charge from r to p in any number of ways, but the potential energy difference is not going to be affected by in which way you bring from r to p. See, for example, you can take this charge q from here and you can go all the way around here to the p, or you can do this way also, but it doesn't matter. The electric potential energy difference only depends on the initial point and the final point. Potential energy difference can be defined in terms of work. So this is how we defined the potential energy difference before. So it depends on what is the work done. So the actual value is not significant because only the difference is significant here. So the only difference of potential energy between the points is significant. If any arbitrary constant is added to the potential energy at every point, it will not change the potential energy difference. This is an obvious point because we have defined that potential energy difference delta U equal to up minus ur. Now we are adding a constant to the potential energy of all the points. So that means the potential energy at the point P is also added with a constant alpha, and the potential energy at the point R is also added with an alpha. So when we add the same constant everywhere, then the difference is not going to change. So that is why the actual value of the potential energy at any point is not significant, only the difference matters. So even if you add a constant, it's not going to change. Then potential energy of charge Q at a point is the work done by the external force in bringing the charge Q from infinity to that point. So now we have defined potential energy difference between 2 points UP and UR. What if I ask you what is the potential energy at a particular point? So to find at the particular point P, we can assume R to be infinity. So the work done in bringing a charge from infinity to a point P is given as the potential energy of charge Q at that point P. So in this case, work done Rp, instead of WRP, we have infinity instead of R place. So W infinity and P equal to UP minus U infinity, which is equal to UP, because we assume that U infinity is 0. So what we are doing in this case is, here we have a reference point as R. We are bringing the charge from R to P. In this case, instead of that reference point UR, we are making it 0. So we are assuming that the charge is somewhere far away from this capital Q. So it's at an infinite position. So in this case, the potential is 0. So we are just making this value as 0. So W infinity P equal to UP. This is how we define the potential energy of charge at a particular point P. Now what is electrostatic potential? So we defined what is potential energy as the work done in bringing a charge q from one point to another point. Now this work done is going to be dependent on the charge q also, because it's obvious, because if you bring a bigger charge you need to do a lot of work. So if you divide this work done by the amount of charge q, then you get this value as electrostatic potential V. So I'll repeat this. If this work is divided by the amount of charge q, the resulting quantity is independent of q. See, for example, if you are doing some work against a field to bring a charge to a particular point, then you need to, that is called potential energy. So if this quantity depends on the charge q also, but you want a general quantity which does not depend on q, what you do is you divide this potential energy by the amount of charge, then you get electrostatic potential V. So electrostatic potential V is defined as potential energy divided by q. So in this case, work done by an external force in bringing a unit positive charge. So here you remember that this is unit positive charge. This is not just any charge q. So this is unit positive charge. Instead of q, we are making it unit positive. That is given by potential difference. So Vp minus Vr equal to Up minus Ur divided by Q. So work done by an external force in bringing a unit positive charge from infinity to a point equal to electrostatic potential V at that point. So here this is a representation how work done on a test charge q by the electrostatic field due to any given charge configuration depends only on its initial and final positions and not on the path taken. For example, if this is a particular charge configuration and this is exerting a field at all the points, right? So we know how to calculate this field also. So there is a particular charge configuration, it's going to have some field. So if you want to bring a charge from a point R to a point P, you need to do some work done. So that work done depends only on the points R and P. It does not depend on the path that you are taking. So you can either bring this charge along this path or straight, or this path or this path, and all of these paths are going to take the exact same amount of work. Okay, now we are going to calculate what is the electrostatic potential of a point charge. So there is a point charge capital Q here, and we are going to calculate what is the electrostatic potential at this point P. So what do we mean by electrostatic potential? It means that if I want to bring a unit positive charge from infinity to this point P, how much work I have to do. So that is the definition of electrostatic potential at this point. So we are going to calculate the work done in bringing the positive test charge Q from infinity to the point P. So the work done against the repulsive test charge is positive because this is positive and test charge is always positive. So you are bringing a charge, positive charge, against the repulsive force of this positive charge. So you are going to do some work on this. At some intermediate point P dash on the path, the electrostatic force on a unit positive charge is given by Q multiplied by 1 divided by 4 pi epsilon naught R dash squared into R cap. So this is the electrostatic force on a unit positive charge. How are we getting this equation? This is coming from the Coulomb's law. Coulomb's law says Q1 Q2 by R squared 1 by 4 pi epsilon naught into Q1 Q2 by R squared. In this case, instead of Q2 we have 1 because it's a unit positive charge, and instead of R squared we have R dash squared. So we are in the process of bringing this charge from infinity to the point P, and in between we are stopping at the point P dash, where the distance from Q and P dash is R dash, and we are looking at what is the electrostatic force at this particular point. So the force is given by this equation from Coulomb's law. Now what we are doing, if this is the force, if I am bringing this making this small displacement delta R dash, what will be the work done? So this is the electric force against which I am doing the work. So work done will be electric force multiplied by the distance, and there is a negative sign here because we are doing work against the electric field. So delta W is the work done in bringing this charge between this distance, that is given by this factor Q by 4 pi epsilon naught into R squared into R cap multiplied by this distance delta R dash, and that is also along the R cap distance. That is why we don't have a vector here, because work done is a scalar quantity. And now Okay, so this is a small elemental distance and we calculated the work done for this. Now we want to integrate this quantity and calculate what is the total work done in bringing the charge from infinity to the point P. So integral of this quantity minus we can take outside and bringing the charge from infinity to R. So Q divided by 4 pi epsilon naught R dash squared into dr. So if we integrate it, then we get this quantity Q by 4 pi epsilon naught into R dash, and minus sign gets cancelled with the integration. Then we get Q by 4 pi epsilon naught into R. So this is the value of the work done at a particular point. So that means it is the electrostatic potential energy at that particular point. So V of R, electrostatic potential at this particular point, is given by Q by 4 pi epsilon naught into R. So this is the electrostatic potential of a point charge. Okay, so now if you look at this equation and compare it with the electric field, you know electric field follows inverse square law, so it means it follows an 1 by r squared relation, but V of R, that is the potential, it follows 1 by r. So that is what is shown here. In the y-axis we have electric field and the potential, in the x-axis we have r. So as r increases, E drops down as 1 by r squared while V drops down as 1 by r. So V takes longer time to drop compared to E. So this is just a comparison between electric field and how electric potential, how they behave with respect to R. Okay, so we talked about a single charge so far, and now we want to know what is the electrostatic potential of a dipole. So write the potential due to the dipole at point P by using the superposition principle. So whenever we have more than one charges, we obviously use the superposition principle, and so by using superposition principle, what we can do, we can just take one charge and find out what is the potential at this point P, and while ignoring the other charge. Then again we can ignore this first charge and take this charge and find out what's the potential at this point, and we can take the sum of these two, then we will get the final potential. And in this case I want to mention that electric potential is a scalar quantity, so you don't have to worry about the direction in here in this case. So the potential due to a dipole is the sum of potential due to the charges plus q and minus q. And if we look at this figure, we already know what is 2a is the separation between the charges, p is the electric dipole moment, and theta is just this angle which r makes with the dipole moment. R is the distance from the center to the point P where we are calculating the electrostatic potential. Let's see how to do this. So we know the formula for V of R for a single charge as Q by 4 pi epsilon naught into R, which we saw in the last slide. So we are going to apply the same formula and find out the sum of both. So V of R for a positive charge is given by 1 by 4 pi epsilon naught into Q by R1, plus it should be plus and V of R for the negative charge. Since minus Q is there, then we have a minus here. So it is actually the sum of both the potentials, and since there is a minus, we have a minus in between. Okay, so now we are going to simplify this by using this relation R1 square equal to R squared plus A squared minus 2AR cos theta. This comes from this diagram. Here R1 is this distance which can be expressed as R plus A. So R1 square is nothing but R plus A the whole square, which is nothing but R squared plus A squared minus 2AR cos theta. It will be 2A dot R, and the angle between A and R is theta, so we have 2AR cos theta. Similarly, R2 square is given by R squared plus A squared plus 2AR cos theta. Now we are just going to apply this. Let's just take R1 squared and take R squared outside. Then what do we get here? Take just this equation and take R squared outside the bracket. Then we have 1 here, and where we have A square, we have A squared by R squared minus 2A R cos theta by R squared. R and R squared gets cancelled, so we get 2A cos theta by R. So in this case we are going to ignore this term A squared by R squared, because A is very small compared to R, because R is the distance between the center of the dipole and the point P. A is the separation between the dipole, and since A is extremely small compared to R, we are ignoring this constant, this coefficient. Then we get R squared into 1 minus 2A cos theta by R. So similarly, if we do the same thing for this equation, we get R2 square equal to R square into 1 plus 2A cos theta by R. So now what we are going to do is we are going to expand these terms by using binomial theorem, and we are just going to keep the first order terms. Then we end up with this kind of equation: 1 by r into 1 minus 2a cos theta by r the whole power minus 1 by 2. So this is the equation which we have from the previous case, and we are going to expand this by using binomial theorem. Then we will get this 1 by r into 1 plus a by r into cos theta. There will be so many terms above this, and we are ignoring all of them, and we are just keeping the first order term. This is an approximation. That's why we have approximate signs here. Okay, now what we are going to do is we are going to apply this in the previous equation. So when you substitute this in the previous equation and rearrange the equation, then you get v equal to q by 4 pi epsilon naught into 2a cos theta by r squared, which is equal to, we know 2a and q is nothing but p, because p is the dipole moment, which is equal to one of the charges multiplied by the distance. So p equal to 2a into q so we are substituting for 2aq equal to p. Then we get p cos theta by 4 pi epsilon naught into r squared. So in this case we have p into cos theta, which can be written as p dot r, because theta is nothing but the angle between p and r. So if you have angle between p and r as theta, then you can write p cos theta as p dot r cap, because r cap does not have a magnitude is 1, so it's not going to affect this. So this is the final expression for v at the point r from a dipole. So this is the electric potential of a dipole at a point P, and this condition is important. This is valid only when r is much greater than a, because then we took the liberty of ignoring a squared by r squared in the equation. So now we are going to approximate this further, and we will say what happens when theta becomes 0 and pi. So in this case, this becomes cos theta becomes 1. So we get v equal to plus or minus 1 by 4 pi epsilon naught into pr squared. We are just applying theta equal to 0 in this case and pi in this case. Then we get plus or minus 1 by 4 pi epsilon naught into p by r squared. Okay, now we are going to see what is the electrostatic potential of a system of charges. So we talked about the dipole in the previous case, and we are going to talk about what if we have more than two charges now. Okay, so again we are going to apply the superposition principle here. So we are going to take each charge and calculate what is the sum of the charge. So the first step will be to calculate what is the potential due to charge q1. So we know the formula from the previous slides. We know v of r equal to 1 by 4 pi epsilon naught into q by r for a point charge. So we are going to do the same thing, and then for similarly we are going to write what is the potential due to v2 and what is the potential due to v3. So this is applying superposition principle. So by the superposition principle, the potential V at P due to the total charge configuration is the algebraic sum of the potentials due to the individual charges. So what we are going to do is, it's very simple. We are going to consider the potential of each charges and add them all up. In the case of electric field, we had the difficulty with the vectors. We had to be careful about the direction, but now you just have to worry about the sign of the charges. You don't have to worry about the direction, because this is a scalar quantity. So V equal to V1 plus V2 plus up to Vn if you have n number of charges. Similarly, just apply the equations for V1, V2 and Vn. So finally you have 1 by 4 pi epsilon naught into Q1 by R1p plus Q2 by R2p plus etc. up to Qn divided by Rnp. So the distances R1p, R2p are nothing but the distances of the point P from individual charges. So for a uniformly charged spherical shell, we have V equal to 1 by 4 pi epsilon naught into Q by R, where R is much greater than capital R, that is the radius of the shell. So in this case what we are doing is, if you have a uniformly charged spherical shell, you can consider this as a point charge, given that the point where you are calculating the electric field potential is much larger compared to the radius of the spherical shell. Okay. So we are going to talk about equipotential surfaces. So from the name itself you understand what is equipotential surface. it says something about equivalent and something about the potential and something about a surface. So we can say that these are surfaces with equal potential. So these are surfaces with the constant value of potential at all points on the surface. So these are just surfaces. In all the points, the potential is going to be constant. So that is the definition of equipotential surfaces. So there is no potential difference between 2 points on an equipotential surface. So what does it really mean? If there is no potential difference, then it means that there is no work done. That means you don't have to do any work if you want to move the charge along that equipotential surface. So, okay. So this is the definition of equipotential surface. You don't have to do any work to move the charge in an equipotential surface. We know that potential for a point charge is given by this equation, q by 4 pi epsilon naught into r. So if you look at the right hand side, it depends on q and r. If you have a fixed charge q, then it depends only on r. So can we say that if you look at this potential at a fixed distance r, and if you move around this charge, everywhere the potential value is going to be same. Like if this is 2 dimension, if I draw a circle around this with radius r, that circle is going to have the same potential everywhere. And if you just imagine the circle to be in 3 dimension, a spherical shell around this charge q, everywhere on the surface of the spherical shell, the potential value is going to be same. So this particular shell can be an equipotential surface. So that's what is shown here. We have a charge q, and around this we have so many concentric spherical shells, and all of them represent one individual equipotential surfaces. So for example, if I bring another charge into one surface here, and if I move the charge along the spherical shell, let's say this particular spherical shell, I don't have to do any work because the potential is same everywhere on the surface. And okay, now we have drawn the electric fields here, and we have also drawn the equipotential surfaces for the same charge. If you merge this with this, you will understand this. The field lines are always outward normal to the equipotential surfaces. That means they are perpendicular to the equipotential surfaces. So the electric field lines for a single charge q are radial lines starting from or ending at the charge. The electric field at every point is normal to the equipotential surface passing through the point, because this electric field is going to be normal to the surface at every point. So for any charge configuration, equipotential surface through a point is normal to the electric field at that point. So this is also an important point. Since equipotential surface is at equal distances, and electric field is always going to be normal to the surface. Imagine if it is not normal, then it means that the electric field will also have a tangential component along the surface. And if there is an electric field along the surface, then the work done cannot be zero along the surface. Since work done is zero in the equipotential surface everywhere, then there cannot be any tangential component of electric field. So electric field will only have the perpendicular component. Let's see how it is. So if these these rectangles are the equipotential surfaces, the electric field is going through like this, and it will always be perpendicular to the equipotential surface. Just like how I explained, if there is a tangential component here, let's say there is a tangential component here which is not perpendicular to the surface, then there has to be some work done. If I want to move the charge along the surface, I have to do some work. So in this case, since there is no work required and equipotential surfaces have equal potential everywhere, so the electric field has to be zero along the tangential component, so it has only perpendicular component. Okay, now that we defined equipotential surfaces, and we also know what is an electric field, and we know that now the electric field is going to be always perpendicular to the equipotential surface. Now we are going to find the relation between the field and the potential. So a unit positive charge is moved from the surface B to surface A along the perpendicular line against the electric field. So we have two equipotential surfaces, one at a potential of V and another at a potential of V plus delta V, and our aim is to move the charge from B to surface A. so B to surface A along the perpendicular line against the field. So field is going upward, so we are moving the charge from B to A against the field. So in this case the work done is E into delta L, delta L being the perpendicular distance between the two surfaces. So now the work done equals the potential difference between the two sheets or two surfaces. So the potential difference between VA and VB. So in this case the work done is equal to modulus of E into delta L, that is electric field and the distance, and also this work is equal to the potential difference, which is nothing but V minus V plus delta V, which is nothing but minus delta V. So the potential of V minus the potential at B. So now you just bring this delta L to the right hand side. So you have E equal to minus delta V by delta L. So what does this tell you? The electric field, magnitude of the electric field is equal to the difference in V when you move from one sheet to the other, one equipotential surface to the other. So E equal to minus delta V by delta L, or we can say plus modulus of delta V by delta L. So electric field is in the direction in which the potential decreases the steepest. That's why we have a negative sign here. So wherever electric potential is decreasing the steepest, the slope is higher, then there we have the electric field. So the magnitude of the electric field is given by the change in the magnitude of potential per unit displacement normal to the equipotential surface at that point. So this is just explaining this equation. So the magnitude of electric field is equal to the rate of change of potential with respect to the perpendicular distance. So for example, if we are moving from the point B to A, what is the change in the potential with respect to delta L? That gives the value of the electric field. So the magnitude of potential per unit displacement normal to the equipotential surface. Okay, now we are going to talk about the potential energy of a system of charges. So far we talked about electrostatic potential alone, and now we are going to talk about what is the potential energy. In the beginning itself we talked about potential energy. Potential energy is the work done in moving a charge Q from one place to another. Potential is the work done in moving the unit test charge from one place to another. So in this case we have two charges and 3 charges here, and we are going to see what is the potential energy of the system of 2 charges and 3 charges. So what do I mean by the potential energy of a system of charges? It means to assemble these 2 charges together at this particular distance, how much work is done. That work is stored in the system. See, for example, if I bring 2 positive charges closer together by doing some external work and keep them together, and if I release it, the energy that is stored as potential energy will be converted into kinetic energy. For example, when you throw a ball up again, you do some work against the gravitational potential energy, so gravitational field, so there is higher potential energy at the top. When the ball comes down, that potential energy is converted into kinetic energy, right? So the same thing applies here. So to bring charges together, you need to do some work, and that work is converted into the potential energy of the system. So how do we find that? So first, let's say V1 equal to Q1 by 4 pi epsilon naught into R1P. So work done on Q2. So for example, you are bringing, let's say there is a charge Q1 already there, and you're bringing another charge Q2 into the field created by Q1. So in this case, you need to multiply Q2 with the V1, because V1 is the potential that is already there, and you're bringing another charge Q2. So U is equal to Q into V. So you're multiplying this Q2 with the V1 which is already present. So 1 by 4 pi epsilon naught into Q1 Q2 by R squared. So U is nothing but 1 by 4 pi epsilon naught into Q1 Q2 by R12 in this case. So the potential energy of a system of 2 charges is this. And now we will just go ahead and do this with the 3 charges. Now I already assembled 2 charges and I have the potential energy of this much. So this much is the work done in assembling the 2 charges. Now what if I bring another third charge? What happens? So first, when I bring the second charge, it experiences the field due to the first charge in the form of this potential. So we have this equation 1 by 4 pi epsilon naught into q1 q2 by r squared. See, first let's assume that q1 is already there and now we are bringing q2. So when we bring q2, the work done will be q2 into v1, which is equal to 1 by 4 pi epsilon naught into q1 q2 by r12. Now when we are bringing, so this is the potential due to both the charges. So how we get this charge, how we get this v value? By superposition principle. See, first we have charge q1, let's say first we have charge q1 and we are bringing another charge q2, and the work done in assembling these two charges is given by this value. Now we are bringing another charge q3 here, and this q3 will experience a potential created due to both these charges. So that potential is given by V12. So the potential created due to both these charges, which is given by 1 by 4 pi epsilon naught into Q1 R1P plus Q2 R2P. Now this Q3, to bring this Q3 into this position, you need to do work which is equal to Q3 multiplied by V12 of R3, because that much work we need to do to bring this Q3. So Q3 V123 equal to 1 by 4 pi epsilon naught into Q1 Q3 by R13 plus Q2 Q3 by R23. So the total work in assembling the charges is going to be U equal to the first term here, because first when you are bringing q1 here, there are no other charges present, so you are not doing any work, so you can ignore this. But when you bring q2 here, you are doing this much work, so that is given by this term 1 by 4 pi epsilon naught into q1 q2 by r12. And when you are bringing the charge q3, you are doing this much work. So that is the potential energy now, which is equal to q1 q3 by r13 plus q2 q3 by r23. So the total potential energy of a system of 3 charges is given by 1 by 4 pi epsilon naught into q1 q2 by r12 plus q1 q3 by r13 plus q2 q3 by r13. So the potential energy is a characteristic of the configuration, not the way it was achieved. So this is again an important point. You can bring q1 first and then q2 second and q3 third. In that case, the potential energy is this much. But if you bring q1 first and q3 second and q2 third, in that case also this will be the same potential energy, because this is the potential energy of the system of this configuration, the final state of this configuration. It doesn't matter how you arrange these charges and how you achieve this configuration. So again, like we discussed, the potential energy depends only on the initial and final points. It doesn't depend on the path. So this is similar to that. So this is the potential energy of the system of charges. Okay. Now potential energy in an external field. So far we talked about potential energy of individual charges. So there was no external field there. But if there is an external field, how the potential energy of the system is going to change. So the potential energy of a single charge, potential energy of a charge q at r is given by the product of charge and the potential at that point v of r. So if I am bringing the charge q, when there is already potential V present, the potential energy of this particular single charge to be at that point is Q into V of R. And the potential energy of a system of 2 charges in an electric field, potential energy of charges Q1 and Q2 at R in an external field is given by, okay, we are going to calculate this. So first we are talking about potential energy of the single charge in an external field. Now potential energy of 2 charges, we already discussed this. So Q2 into VR2 will be the work done. So this is the total potential energy of the system of 2 charges. This is the work done on Q2 against the field due to Q1. So Q1 already creates a field, and against that we are doing some work. So the work done in bringing Q2 is Q1 Q2 by 4 pi epsilon naught into R12. So now, already there is a charge q1 that exerts a potential, and because of that this is the potential energy, and V is the potential already present due to the external field. So the total work done on q2 will be q2 V of r2 plus q1 q2 by 4 pi epsilon naught into r2. So this is the total potential energy of the system. Total work done in assembling this configuration when there is already an external field present. So in the previous cases, we ignored that external field. We talked about only the Q1, Q2 and Q3 charges. So when we are assembling the charges, what is the potential energy involved? But in this case, there is already an electric field present. So even when you are bringing the first charge itself, you have to do some work against it. That is why we have two terms in this case. Okay, so now this is the final term. So this is the final term of this two charge configurations in an external electric field. So let's assume this V is created due to the external field. So this Q1 VR1 is the work done in bringing the charge Q1 in this external field, plus Q2 VFR2 is the work done in bringing the charge Q2 in this external field, and Q1 Q2 by 4 pi epsilon naught R12 is the potential energy between the two charges. So Q2 experiences the field created due to Q1, and that term is given by this. That's why this is the final term. Okay. Now, okay, we talked about assembling the charges in an external electric field Q1 and Q2. Now, what if we bring a charge dipole in an external electric field? So we know dipole has charges plus Q and minus Q, and when we place them in an electric field, it experiences a torque, and the torque is given by P cross E. P is the electric dipole moment and E is the electric field. And we know all these terms. Theta is the angle between the electric field and the dipole, and A is the distance, 2A is the distance, and in this case X is this way and E is along X. So an external torque delta tau external is applied in such a way that it rotates the dipole from angle theta 0 to an angle theta 1 at an infinitesimal angular speed without angular acceleration. So in this case, the electric field tries to rotate this dipole, and what if we do some external work by giving an external torque and rotate this from an angle theta 0 to theta 1. So the work done is going to be integral of theta 0 to theta 1 tau external of theta into d theta. This is similar to FDR integral r to p in the first slide which we saw. So work done is always going to be equal to force multiplied by the distance. In this case, instead of force we have torque, and instead of distance we have angular distance. So this is equal to tau external is given by P cross E. So we have P sin theta into d theta. So theta goes from theta 0 to theta 1. PE we can take it out, and sin theta is cos theta minus cos theta. So we have P into cos theta 0 minus cos theta 1. So this particular work is stored as the potential energy of the system. So this is the work that is needed to rotate the dipole from theta 0 to theta 1. If you rotate this dipole by giving an external torque, this particular work done is stored as a potential energy of the system. So the potential energy is 0 when the angle theta 0 is pi by 2. So in the previous equation, we have cos theta 1 minus cos theta 0, and if you have pi by 2 for cos theta 0, then you have cos pi by 2 is 1, then you have minus P cos theta. Minus P cos theta is nothing but minus P dot E. So U as a function of theta is equal to minus P dot E. So it depends on the magnitude of dipole moment and the magnitude of electric field and also the angle between them. So the dot product of these two. So this is the potential energy when you keep the dipole in an electric field. So again, we will do the same thing what we did in the previous cases. When we bring this dipole from each charge and keep this in this electric field. So let's say first we are bringing the charge plus Q. It experiences a potential V of R1. So the potential is potential energy is Q into V of R1. Plus it has to be Q into V of R2 when you bring the other charge. But the other charge is negative, so we have minus Q into V of R2, and the interaction potential, that is the potential experienced by the second charge because of the presence of the first charge. Like in the previous case we had Q and Q2 by 4 pi epsilon naught into R. So R is nothing but the distance between them. So in this case we have minus, because the product of Q and minus Q is minus Q square. So minus Q square divided by 4 pi epsilon naught into 2A. So now this U dash of theta, that is equal to, instead of this first two terms we will substitute minus P into E, because that is the potential energy of keeping this dipole in this external field when we are ignoring the interaction between them. So this is the potential energy of this configuration. So the potential energy of this configuration in an electric field is given by minus P cos theta minus Q squared by 4 pi epsilon naught into 2A. So if you rearrange this and simplify this, it is going to be minus P dot E minus Q squared by 4 pi epsilon naught into 2A. So this is the potential energy of the overall configuration. Thank you.
Why waste time in commute and spend a lot of money for NEET UG coaching? Parents, do you want your kids to achieve top scores in NEET? India's leading online NEET coaching, 100% success. NEET UG. TeenEinstein.com. At TeenEinstein, we focus on NEET coaching from Class 6 to Class 12. We think you'll like it. Our teachers are mostly PhDs in physics, maths, chemistry, botany and zoology, with lots of years of teaching experience for Class 6 to Class 12. Thousands of videos, quiz, MCQs. We provide a daily worksheet of 30 questions on each topic: math, physics, chemistry and biology, for rigorous practice, concept understanding, evaluation, quizzes and thousands of videos. Limited offer, 40,000 per year. Book your class. TeenEinstein.com. Contact 99402 49720.